This is a quick trick that I just mentioned here, but do you know this is not a Drake specific thing? This is just a GitHub thing, and I guess Microsoft, I think, bought GitHub. I'm not wrong about that, but if you have any GitHub URL, if you have just GitHub open in your browser, and you want to search the code, browse the code, just replace the GitHub with GitHub 1S, and it'll pull up a Visual Studio client in your browser, and you can just like quickly search and whatever. So if you want to like quickly poke around in the source code for Drake, even if you're not super comfortable in C++, there's often like use cases of all the different methods are all searchable inside there, and even the C++ and Python syntax is not very different, so possibly to a fault. Good. Okay, so today I want to sort of launch into the bigger conversation about control for manipulation. We started it by talking about manipulator control last time, but I want to go from manipulator control last time to the more sort of full discussion of feedback control for manipulation. And let me make sure that distinction is clear, because it looks kind of the same words. Let me just make sure my intent is clear, even if you might recommend some better words for it. But when we were talking about manipulator control, this was only controlling the robot. And that was important, right? That made a lot of things a lot easier. Remember, we were using, the reason I call it manipulator control is it leans so heavily on the manipulator equations, which was just my mass times acceleration equals the sum of the forces, which looked like mq v dot. It has a particular form in the manipulator equations, but something like this, okay? Where this was the mass times acceleration terms, this is gravity force, this was maybe damping or friction or other things. Importantly, this was my torque input. These were maybe my contact forces or other applied forces that were described in a Cartesian frame. Okay, and we worked with those equations a bunch last time. You could also, so I hope you see that as mass times acceleration is the sum of the forces. You could also see this as just a differential equation, which looks like f of xu, where my x is q and v, and so this is just x, the equation for x dot. This is half of the equation for x dot. So you could say I would write this as that equation is similarly v dot is f of q v u. The other one that I need is that q dot is just v dot v, and that together is my upside down x dot. Yeah? Okay. But there's a bunch of things that this distinction of only control the robot was baked into what we did there. So in particular, the way I've written it here, I had that the dimension of q equals the dimension of v, at least for my Revolut joint robots, equals the dimension of u. And even more than that, just the way I wrote in u is it entered linearly like this well, it always enters linearly, but there's no modifiers there. So it just came in, and you can use any U to directly control V dot. So that, I teach a whole class on the difference between fully actuated and underactuated, but that makes these equations a fully actuated system. Okay, and it's a particularly easy one to control in that form. For instance, we saw that PD control worked. We saw inverse dynamics control, stiffness control. We saw a bunch of things that worked pretty easily, in part because I had U that had direct control on V dot. Also, this was one important point. A second important point is that MQ and all these other terms were known, or at least estimated. Pretty well. Let's say estimated well. Okay. In practice, we have good system identification tools that if I have an Iwa or a Franca or some other robot, I can move it around a little bit. I can get very accurate estimates of M. And in fact, KUKA has done that for us. And they are doing the low-level control that's canceling that out for us. Okay, there are things that can make that control a little easier, like torque limits, and a little more interesting, like torque limits or other bits. But out of the box, that was a class of control problems that we know a lot about, and we have very good solutions for. We can command fast trajectories and track them very accurately. We can control contact forces pretty accurately. But that is not representative of the bigger problem of feedback control for manipulation, right? Right, so the bigger problem is to not just control the state of the robot, but to control the state of the robot and, more importantly, the state of the world. And a lot of those assumptions that were fundamental in the way we wrote our controllers become no longer true. And I want to spend a little time talking about the ways that those are not true and the ways that those complicate control. Okay, so whereas before we had X was, let me just say Q robot, maybe, and V robot was our state before. Now we're going to at least something that has, in that example, the state of the brick in the state space. But unfortunately, our U is still just U robot. I picked up more degrees of freedom that I'm trying to control, but I didn't actually pick up more actuators by which to control it. Okay, so that is now another differential equation, which I could write as my same sort of V dot is F of Q V U. It's still a differential equation in all of those, but the dimension of Q is now strictly greater than the dimension of U, and that makes control a lot more interesting, a lot harder. So that's where you come into underactuated systems. Okay, but that's not the only way that the problem got a lot more interesting if we start trying to control the world. There's a bunch more, and I just kind of want to I want to talk through them and make sure we appreciate those. Okay. So even if we assume perfect perception, so let's ignore the perception problem for a second. So let's say that I have a perception system that's reading my cameras or whatever, my perception system that's outputting some estimate of my state. And perfect perception for me means that x hat is just outputting x directly. In simulation, we could just be using the cheat port and asking multibody, what is the true state? Okay. So still the problem is rich because it's underactuated. But also because the only way, if you look at the equations, U on the robot is what you get to control. Your goal is to control, let's say, Q brick. If you look at the way those equations come together, the only way that U gets over to control Q is through the contact forces. The equations of motion are, in some sense, decoupled. They're only coupled through the contact forces. So you have to do the control through the contact forces. Okay, so if I were to, when I do write the equations of motion for that robot plus brick system, it actually still looks like the manipulator equations. Those equations are still valid. But there's an extra set of equations let me put a little b underneath all of these. There's a new set of equations for the brick variables. You can write force equals mass times acceleration for this too. You have the gravity of the brick. B is for brick, okay? I also have the robot ones. Okay, and the whole thing together is one big set of equations that I simulate with my integration methods. They are beautifully decoupled, like as a structure you'd want in your equations to make your math better and stuff like this. It's beautiful that these equations actually don't depend on the robot, and these equations don't depend on the brick, except for the one extra thing, which is that the forces here on the robot at C have to be equal and opposite of the forces on the brick. There's one extra constraint that couples them together, which is that those two are equal and opposite. But if you think now as the job, like before what we were doing, right, when we were working with those equations, is we would choose a U that would cancel out some dynamics, put in some spring-like dynamics to make it feel like an impedance or a stiffness, or there was a bunch of tricks we did. Those are not readily available now because the only place that my U came in was in the robot equations, my control input. And the only way that those U's get through to the other side is through the forces. Is that clear? And those forces are fickle. They're subject to a friction cone constraint. They turn off if you're not actually touching things, right? That's kind of annoying. You can push, but you can't pull unless you got a suction gripper. Okay, so this is not just, this is like not as direct of a way to control those variables as just having a torque directly on the motor. And that complicates. That means you have to, if I want to start having any effect on the brick, I have to touch the brick. I mean, that's obvious in the, in the physical interpretation, and it's visible here in the equations of motion by seeing that the only way that that happens is these forces become non-zero, and that's how it goes across. The fact that those are not only intermittent, it makes things non-smooth because they go from sticking to sliding, or you weren't touching and then you are touching. There's all kinds of interesting stuff that happens with that interface. So those are two big ones. We're suddenly going, if we want to control the world and think about it as a feedback control problem, then we have to think about it being under-actuated, and we have to think about the control through contact. But wait, there's more. It's still harder. So I'm going to spend a little time making you see how hard it is, and then we're going to try to hopefully make it look easy again. Okay? But that way, hopefully we appreciate at the end why the thing that makes it look easy is surprising, I would say. Okay? Unfortunately, perception is not perfect. Right? So if I think about the role of my perception system that's taking, let's say, cameras in, perception, even if I'm trying to estimate the state of both the robot and the brick, right? The way that the perception systems makes errors is pretty non-trivial, and you've seen that already. You've seen, for instance, ICP works spectacularly well, and then it doesn't. And it's not that this is a little bit off, but it would just give you complete garbage on one frame, right? If it loses track, for instance. And that's true of many camera-based perception systems. They can often work spectacularly well, but then fail catastrophically. So a lot of our traditional controls, you might try to say that this variable is maybe has Gaussian noise on it or something like that. And you could think about this as part of a Kalman filter framework, if you know that. Okay, but perception systems make very non-Gaussian types of errors. In particular, if you have a linear Gaussian system, if my equations happened to be linear and my noise happened to be Gaussian, those are not linear equations, those are nonlinear equations, and hidden inside there's sines and cosines and the like, right? They're not linear. And the system was Gaussian, then I could say that if x hat was just sort of the expected value of x already, we're in pretty good shape. And maybe I have to also, I want the variance for linear Gaussian, you don't actually need even the variance, but maybe the variance of x can be a useful thing to estimate too. And even though those equations are not linear Gaussian, if you're just controlling the robot, but not the object, then we saw cases where we could use feedback to make the equations look very linear. And in fact, these linear Gaussian tools that have grown up in control theory work really pretty well for a robot. It's pretty reasonable to think about estimating just the mean of the joint positions and velocities and possibly having a covariance of the joints and joint velocities. But once you add in the brick, all bets are off, because suddenly you're going, your only sensors measuring the brick, unless you're in a strangely instrumented environment, are like your cameras, maybe your contact sensors and the like, and those are not sensors that give you sort of nice Gaussian noise properties. And you remember that, right? So we talked about, for instance, when we were talking about perception, the types of uncertainty you might have of a perception. I was going to bring a coffee mug down. I forgot. Shoot. But if you can see the handle of the mug, then maybe you have pretty small uncertainty. But even if your sensors were perfect and your perception system was doing as best as it possibly could, if the handle of the mug is not visible to you, then you cannot estimate the orientation of the mug with absolute certainty. You have to somehow communicate that I only know the orientation of the mug up to some uncertainty ellipses. Partial observability also causes non-Gaussian uncertainty. How many people know what a POMDP is? A partially observable Markov decision process. If you like POMDPs, you could just say, it's a POMDP, right? I'm not advertising this as a path of happiness, so if you don't know what a POMDP is, you're all good. It's useful to, I do think the language of POMDPs is very powerful and helps us understand the problem, but I'm not going to give a whole lecture on it right now. Okay, right, but more generally, if I think of my system as a POMDP, I'll give you the language. It's a partially observable Markov decision process. It's a fancy way to say that I have a dynamical system that has some stochasticity, and I don't get to see all of the states directly. Okay? But for those of you that do know what a POMDP is, I want to connect to that real quick. And I think in general, in the general POMDP case, what we should say is that the output of our perception system should be not just X, but a whole probability distribution over X. And that's the kind of thing that CosNet tries to output, and a lot of perception systems these days will try to output, right? This would be like a probability distribution or a belief distribution over X. From the mathematics of partially observable Markov decision processes, we know that that is a reasonable answer. That's a complete answer. If I can put out an entire probability distribution, and if I can write a controller that can consume that entire distribution and make good decisions, then we know that is sufficient for making optimal decisions, even in a partially observable setting. But this requirement of outputting an entire probability distribution is a large requirement. And in particular, designing a controller that can reason about that is very hard. Okay? It's also sort of interesting that it's not, I'm going to say it, I guess, later, but having a perception system that gives me the complete output of all the possible states of the world is sufficient to make optimal decisions. But we've, over and over and over ago, we've seen people write great controllers, like spot opening the door or I call them the robot whisperers, right? Incredible controllers that do not use this as an input, but use a much smaller amount of information from the observations as input. So even though this is sufficient to be optimal, it's probably a lot more than you need. Okay, and that's an important big theme. So this is a mathematically powerful tool chain, but it's probably more than we really need or want. I would say, though, that even the POMDP language, as I've written it there, can be insufficient for the manipulation problem, because it made there's one place where it has a weakness. Everything is a POMDP, I give you that. But it's a POMDP in some state space. And if I've chosen some representation of my state, x, and written a probability distribution over x, I may or may not have gotten the right state, right? So even p of x might might not capture the true state. And this is I actually mean this in a deep and important way. I'm not trying to be flippant about it, right? I think most of the control theory that we've done or sort of in life has assumed that we know at least what the state representation is. That you know that, for instance, the joint angles of my robot, the joint velocities of my robot, the quaternion that's specifying the quaternion plus translation that specifies the pose of the brick plus its spatial velocities, that is the right state. And if I write a distribution over state, then I can solve that, then I've somehow solved the problem. But that broke down when we started thinking about category level manipulation, right? As soon as you say you have uncertainty about the geometry of the object, then again, suddenly, where does the uncertainty about the geometry fit in x if I just had x being the positions and velocities, right? So x somehow needs to encode uncertainty about geometry. Maybe even uncertainty about the mass. Not for that particular type of task. You didn't need to know the mass, you just needed to know the geometry, really. But certainly there are tasks like the force-controlled tasks we talked about where the mass estimates are important and the like, right? And this is, I think, maybe one of the biggest things that we've done. We've railroaded ourselves a little bit in the sort of classic control is for robots, we say, okay, well, we're going to estimate a distribution over the possible joint positions and velocities, world positions and velocities. And we haven't sort of naturally encoded geometry and mass uncertainty and the like. So people are really excited these days about, let's say, well, maybe I've got an implicit representation of geometry, right? And maybe if I have a nerf or a sign distance function or something like this, and I can use that in my state representation, then I can somehow write controllers that work for many geometries. And that's a huge, big topic that's hugely important. Okay, but even that can fail, right? So even if I had a beautiful way to write x with positions, velocities of the robot and the brick, and then I have the geometry included and the mass included, there's still, I have only a handful of examples that I always use, but now what if I'm just doing this? Like, okay, I could write positions and velocities of all the pieces, but the number of pieces is breaking, right? And the contact mechanics and that's hard stuff. That's kind of like, if I start writing that down and asking about the dynamics, how they evolve and the state space evolves and stuff, like that just kind of breaks down, right? The way we would write that control problem breaks down. It makes my multi-body head explode. This one does too, right? I mean, if I want to do I consider this like a pinnacle of manipulation. We all do it, a couple times a day, right? But that's incredible. But what is the state of the shoelace? Yes. Do you have the answer? That would be amazing. I'm sorry, Rob.
Why OMDP? Why not MDP if we have the cameras and we can see this?
Okay, great, awesome. So let me come back to that. I'll just do my 3 things, then I'll come back and try to answer that. Yeah. So this, so when you get to deformable objects, then suddenly the state representation question gets really rich again too, right? So we use methods from finite elements and stuff. There's ways to represent the state in order to simulate it, of course. But is that the right state to build a controller, right? I always talk about spreading peanut butter on toast. There's a few of them I feel like kind of capture most of the things. What is the state of the peanut butter? That's ridiculous, right? But that task should be very easy. The way we've typically written down feedback control makes it seem extremely hard. Okay? And people clearly have these strategies, right, where you can kind of feel when the peanut butter clumps up, and there's a lot of, I think, tactile feedback in there, visual feedback that's happening. Probably there's not a finite element or granular media model of the peanut butter in my head. And the last one I always talk about is buttoning my shirt. Okay, so this is a how-to button your shirt. Okay, but if you think about what is required for control, we button our shirts all the time, but probably the first step of buttoning my shirt should not be to completely estimate the entire state of my shirt, right? I have probably a very nice local policy that works with feedback on my fingers or whatever. It's not very visual, I don't think, Okay, so there's something that the clear view of, sort of the mature view of control isn't doing, and that's what I want to kind of talk about today. But so, Robbie, to your question, so why is it, did I say it's a POMDP instead of an MDP? I think there are versions of the manipulation problem that, and maybe when I put the red brick with the sort of cameras all around, I think an MDP would probably describe that very well. But if I were to take my coffee mug and occlude it, put it behind here, right? Then suddenly partial observability has a very physical manifestation, and it happens all the time in manipulation. If I have a hand and I go to pick something up, the hand almost always occludes my head-mounted sensors. It's really annoying. It's like the time where you want the information the most, you've occluded yourself, right? And so people say, oh, I'll put a camera on my hand, but then cameras get blind when you put them too close to an object, right? So partial observability, even if the world didn't start with occlusions and the like, it's a real problem in manipulation. So I think POMDP is the more general framework for that. Thank you for asking. It's good. Okay, so maybe you get my point. It's a hard control problem, even if you knew the state space. You probably have to think about uncertainty over that state space, and guess what? We don't know the state space in a lot of interesting problems. And even trying to know the state space seems like a tall ask. Okay, so what do we do about it? The hope is that some of these tools for machine learning are going to help out. And they've done incredible things over the last few years. And they've kind of come in from the other end. So this is maybe coming from the multi-body equations up and adding all the complexity. And there's another set of tools that have come from, let's start with just images, and start working back towards control. And I would say, the field is kind of like working this way, and we haven't quite met in the middle yet. But I'm optimistic. Like we're pointing at at each other, and coming more and more together. Okay, so if I'm going to do machine learning for it, what's the machine learning problem that I need to solve? Okay, so if I think about the multi-body case again, let's just distinguish a couple of the different control approaches, right? So if I have my plant here, I'll do it in block diagram language, okay? And I have Y here. These are my cameras, for instance, my sensors more generally, cameras. The way I've always talked about this is that I have some internal state inside my system. You have some inputs, you have some outputs. And that's exactly what Drake makes you say, is I've got some state dynamics, I've got an output, I've got an input, okay? The output of the let's say the manipulation station is like the cameras, okay? And it's not, you typically don't have direct access to X. And that's what I'm doing with my perception system. And maybe I'm outputting something like X hat. This is my planning and control, but I'll just write control for now. That goes to you and around. Okay, so I would call this state estimation plus full state feedback architecture, okay, where this is my state estimate and this is my full state feedback here, which takes X hat as an input. The POMDP belief space planning in the language of the diagrams here is a superset of that. But if I think about my perception outputting an entire probability distribution over X, then I have to write some controller that knows how to take that, do something more than just assume I have X given to me, but I've got an entire distribution over X. This is what I get in my sort of POMDP belief space architecture. Belief space is just another name for my estimate over X, my probability distribution. And in this setting, in both of these settings, you know, the perception system maybe could be a Bayes filter if you know about filters, or a Kalman filter is a simple version of a Bayes filter. Just to connect those words if those are something you've thought about. But like I said, this is more than you need for control, right? And I remind us of the, you know, the controller that was written for this is extremely robust. You know, it sort of has a sense that someone could push me with a hockey stick, right? Implicitly. And it's an incredibly good controller. I don't know that it's optimal in any ways, but it's highly functional. And it is not trying to estimate a full belief over the possible environments. It's not trying to estimate with high accuracy the angle of the door handle or the door. It's using a much smaller summary. You know, it's Andy and you know, colleagues, I know it's very distracting, wrote a beautiful controller that used the sensors more directly. They didn't try to estimate the full state of the world. And it works really well. So there's some sense, I think, which is that that picture makes the problem look too hard. So the way we want to think about it today, to sort of launch into our further discussion about control, is to go to the other extreme and appreciate that there's another extreme here, which is, what if I just take my plant, I have my observations coming out Y, and I'm going to go directly from Y to U, okay? Even if these are cameras. And I'll call this output feedback. It's not my name, it's a output feedback control, as opposed to the state feedback control. Okay? When Y are pixels, camera images, let's say. U are torques. People like to call it pixels to torques. It's a really funny, a lot of people say pixels to torques. Some people say it like, it's awesome, pixels to torques. And some people are like, pixels to torques would be the thing no one should ever do, So it's a highly volatile term, but it's like pixels to torques for self-driving sounds kind of scary, but it's a very powerful possible framework. And in particular, if this is a kind of a high rate, if this controller updates frequently, then I would also call it a visuomotor policy. In the manipulation space, we'll call these visuomotor policies. And that's kind of a weird caveat that I'm putting in there, but I just want to distinguish it from, you could make a diagram that looks a little bit like that, that would be a little bit, more of a sense, plan, act, classical architecture. And the type of policies I want to think about today are ones that are looking at the camera all the time and constantly making decisions. Okay, so this of course should just encompass those, right? I could take both of those, write a diagram around it and call it an output feedback, and that's true. But I think this version of the picture opens up the door to different architectures that don't impose that structure. So that's the big question, is what is the right architecture for that kind of, how should we write that down? How should we describe that output feedback policy? Right? And then how do we find its parameters? Once we choose a class of possible output feedback policies, how do we find those parameters? Is that setup clear? The exciting thing, of course, would be if we can go from Y to U without ever having to pick an X. As soon as the human picks an X to represent our intermediate computation in, we've assumed something about the state, and it's not going to spread peanut butter on toast. And that, I don't actually like peanut butter on toast, but that was, but there's something similar to that I would like a robot to do. Okay, here's my opening bid. What if we just say, I want my output to be a direct mapping from, whoops. You could have told me. How about that? A direct mapping from camera images, let's say, directly to torques, okay? And that seems like the architectures that know how to take camera images as input tend to be neural. So I'll go ahead and say that's a neural network, yeah? Probably a deep net, convolutional, or whatever architecture you like, right? This architecture, if we were to just write a function of like a feed-forward network that goes from an image in to a control torque out, the control theorists would call that a static output feedback. Like for a linear system, it would look like instead of negative kx, if you thought about this, it's something that looks like this. Would be a direct linear mapping from observations to inputs. And it turns out, although control theory knows a lot about the static output feedback problem, most of what they know is that it's hard. That even finding this for a linear optimal control problem, finding that k is actually an NP hard problem. So that's not a good sign, but there is a lot known about it. Okay. But let's ignore for a minute the fact that maybe finding the optimal parameters are hard. We'll come back to that. But let's just say, is this class of, what is this class of policies capable of doing? Let's say I had an oracle that would just tell me, these are the weights that are the best controller in this class. You've chosen a number of layers, a number of, an activation method, an activation unit and stuff like that, and then I'm just going to tell you what the weights and biases should be. The best possible. What can that do, right? And what can't it do? What can it do? What can't it do? It can't deal with occlusion, right? So if you had a frame that, if you said, reach for the red brick, and I put the red brick, let's say, behind my laptop screen, then that would be uncertainty or something, or the control through contact. If I had the red brick behind my laptop screen, I said, go ahead and pick it up, then that kind of controller doesn't have any mechanism to sort of reason about, what should it do to pick that up. If you were to watch me take the red brick and put it down there, then you would know there's a red brick there. But if your controller is only able to look at the most recent image in order to make its decisions, it doesn't have that power that you have. It has no memory, no history. Okay? So despite the incredible power of deep networks, a deep network, there's a bunch of things that this isn't going to be able to do. Occlusions is a good one. What's another one? Even if there's no occlusions, there's some things this can't do. If, let's say, y is an image. Almost all of you are like throwing things or catching things or smashing things, right? Mass. You can't get mass, right? So that's right. I mean, so really any dynamics. You could argue that you could get a mass from a statics point of view, right? You could know from a static equilibrium type analysis something about mass. But you can't know velocity, for instance, right? So if I show you a single frame of a ball, and I show you another frame of a ball, and you're only thinking about that, the fact whether it's coming towards me or away from me is completely, I'm oblivious. Yes? Perfect, yes. Right, so there's a natural, that's a great question. So Jenny says, what if I have a history, right? So this would be my second bid, would be, what if I said that u at time n is a function of the image at time n, but maybe a image at time n plus minus 1, maybe some n minus m or something like that. Okay, so that you could do. You could even also do some occlusions, right? Although, if I take the red brick and I show it to you and I put it behind here, you better pick it up in less than m steps, otherwise you're going to forget, right? So. But certainly 2 should be enough, depending on how noisy things are, to estimate a velocity. And more than 2 maybe would allow you to estimate a velocity more robustly, because you'd have enough to sort of estimate covariances and the like. Okay, so this is great. So this is also something that we know a lot about from sort of more general systems theory. This would be a finite impulse response model. There's different names for it, but if it was a linear system, it'd be a finite impulse response model. FIR. People remember FIR filters and the like from, you take signals and systems, yeah? Right, you could call it a moving average filter or something like that, okay? And we know what it can do and what it can't do, right? In particular, it's got a finite impulse. It's got it won't remember things more than capital M, and you have to make an M. When Y is an image, that could get expensive if M gets too big, right? So for long horizon tasks, this might not be a good choice, but for short horizon tasks, it's a perfectly good way to take and give some limited form of memory to a neural network, feed-forward neural network architecture. But I also really like this because this, even though you might not think of it this way, when I start thinking about it this way, and maybe not if I called it a neural network with an image in and whatever, but when I write it this way and I think of it as an impulse response filter, then you realize that this is actually just an opening. I mean, even this one is true. This is a dynamical system. What I want you to start thinking about is that the control policy should be a dynamical system, right? It's a dynamical system that takes y's, a time series of y's in, outputs a time series of u's. And u equals pi of y is one form. This is another form. But more generally, you could make an IIR filter, an infinite impulse response filter. You can do a state space model. And that's exactly what's happening in the neural network world too. And I just want to make sure you see it that way. Because we know a lot about what each of those models can and can't do. And sometimes that gets a little bit hidden in the weights of the neural network, for instance. Okay, so you could do an IIR filter, like a simple change. It's an infinite impulse response filter. Or more generally be called an autoregressive moving average with exogenous inputs. Oh my God, I'm not going to write that. But Rmax, people say, that's like a cool thing to say at parties, right? This would be like an Rmax system that would say, if I wanted to say that U of n, if you want something to have an infinite impulse response, if you want it to have arbitrary history, it turns out you don't have to do much more than that, right? Jenny's proposal was good, and I can just change it just a little bit, and maybe she even meant this. But if I also put in U of n minus 1, okay, and then Y of n minus 1, U of n minus 2, if I just cycle back my outputs, then that system depends, of course, on the weights or whatever, but that system can have an infinite impulse response. Okay? That's a neural architecture you could pick that would have more representational power than that, from finite to infinite. Okay? And the linear systems equivalent of that is like super well understood. More generally, you could write a state space model. Where you could say that U of neural network is, let me call it, that U of n is a function of x of n, and x of pi n plus 1 is some other function of pi n with y coming in. Okay, I could have a neural network that has an internal state. And I could allow that state to evolve with another neural network, for instance. And then I could just have my output be a function of that state. That would be a state space model. Linear state space models are AX plus BU stuff, standard fare. And that's just what a recurrent neural network is doing. For instance, if you know what LSTMs are, long short-term memory. Yeah? Then that's just another representation of a dynamical system. And it has representational power. It similarly has infinite impulse responses, okay? And it can have a long history. That's most notable here is, if I compare this versus this, This has the representational power to remember things for arbitrary durations, right? So if I take that red brick and I put it behind my laptop, then you can just say, I'm going to devote one of the X's to remember that guy put a red brick behind the laptop. And a year later, you come back and say, like, I remember where that red brick is, right? Because you've given yourself that power of memory. This is a scratch pad for memory, right? And it can evolve in beautiful continuous equations. It can be a less beautiful neural network, but still super powerful, exceptionally powerful. But those are standard things. The Kalman filter, state estimation that I talked about here fits into this model. If I said that x hat, I called it x pi here. Okay, that is certainly similar, but it's way cooler if x pi doesn't have any presupposition that x pi should be an estimate of the original state. If no human said what x hat is, but the learning system decided to use x however it needed to reproduce the input-output of the system. Okay, so that's what this suddenly, if I now want to, if we ask how do you find the parameters of this input-output system, whether it's static, FIR, IIR, or state space, then now that becomes a second question. And a good answer to this would be one where you don't have to say what x hat is, or what x pi is. Okay? The simplest form of this would be an imitation learning form, okay? In particular, I would say imitation learning, broadly speaking, slightly oversimplification, but I'd say there's two big classes of imitation learning. One is inverse optimal control, and that's not what I'm going to talk about now, but I don't want to pretend that I'm talking about all of, oops, that was pretty funny. Revealed my biases, I guess. And the other one I'll call behavior cloning. Okay? Just to say that, I mean, imitation learning also is called learning from demonstrations. There's a bunch of buzzwords, but they're all the same thing, roughly. Sometimes you'll just see LFD. Okay, but let's think about the behavior cloning version of the problem. Behavior cloning is actually an old idea that I went back and looked where it started. I found 95. It's an old idea. It's cool now, but it's an old idea of 1995 paper of just behavior cloning. And really, what this is a simple approach where you say, I'm going to treat control design as basically a system identification or a simple supervised learning problem. So if I have a human, let's say, that's trying to control my system, and I have a policy here that I'm trying to fit. It's a dynamic output feedback policy. If I watch the human operate the task and I record the Y's and the U's, the actions that the human took and the observations that they had available, then I can try to do supervised learning to make the policy do the same thing. When it's a recurrent network policy, it's a slightly more interesting supervised learning problem, but we know a lot about how to train recurrent networks for sequence learning like this. Okay? So I don't think many people would say this is like a final answer, but this is a really interesting way to start looking at the problem. And in particular, I think it lets us sort out a lot of the architectural questions of how should we represent our policy? How valuable is it to use cameras on every, at 10 hertz versus at, 1/10 of a hertz? Every 10 seconds, right? And asks a lot of those questions. But a natural question for this, before I get into the details of how we do that, is how do you even get that input, right? So for robots and mobile manipulation, as deep learning started getting good, people started coming up with more and more clever ways to capture humans doing the task where you didn't want to watch, if I watched a human doing this, like on YouTube, if I wanted to watch a human rolling dough, that's a hard problem still to map from a human's controlled torques and a human's real observations into robot actions. It's much easier if you can get a human to operate the robot. And then you watch directly the torques that are being applied from the human's controller, and maybe if you give the human exactly the inputs that the robot's getting, then now you have exactly the input-output data that goes to the human, and you can try to just turn that into a supervised learning problem. And people have been making cooler and cooler versions of this. How many people know that the X Prize, the Avatar X Prize happened this weekend? Yeah? Right? How cool is that? So just this weekend, so the X Prize is like they make these grand challenges about improving the world, and they picked a robot example this year, and it just happened on Friday and Saturday. I won't play the whole thing, but it happens that the way it worked was they had roboticists, that were the judges. This is my friend Jerry Pratt, who's driving. This is the winning company. He was the best driver apparently, and had the system that won by Sven Benke and company. Okay, so there's this whole mock setup where he had to drive up. He was only given even the context of the task by talking to somebody who told him what the rules of the game were. He says, you're going to have to go over here. You're going to have to pick up the cylinder, and only one of the cylinders is heavy and should be placed on this other spot, right? So you have to actually use your force feedback through the avatar in order to know how to complete the task. There was another one, he says, where you're going to pick up some moon rocks or something, and one of them has a particular texture. And you have to put the one with the particular texture over here. And there was a series of pretty complicated things. And I'll forward a bit. He talked for a long time, I guess.
Have you ever noticed it's pretty quick on the commute? That was the HOV lane, so they got right through.
Probably turn that guy off, yeah. So this is the one where he had to pick up something that was a particular weight, and he's strapped into a series that was too light, so he threw it away. Okay. Now he picks up the next one, but he's driving. These are actually just two Panda robots that are in kind of like gravity comp mode, so they can be used like this, like a teach mode. And he's got an exoskeleton hand, and he's driving this thing around and doing super complicated tasks, right, with force feedback, haptic feedback. And he completed the entire course. I don't think they were sure that anybody was going to complete the entire course, but he did, and they did, and they did extremely well. So you should go back and watch the long version of that. One of them that I really like, there was actually an entry by Northeastern that came in third, that Northeastern just across the river. They had this awesome setup with a dexterous hand here. And this is in their lab, but they did very well in the competition too. Similar things, pick up the heavy thermos. He's able to do all kinds of stuff. He shakes hands. Okay, yeah, shakes hands. And off to the side, this is what it looks like, right? He's seeing through the robot eyes and wearing this cool exoskeleton. It's awesome, right? I want one of those in my lab. They're super cool. If we have time at the end, I'll show you my version. not as cool. But you can use it on deep note. It's crowdsourced teleoperation, which is a thing, by the way. People have started companies saying, we're just going to crowdsource teleop and learn how to control your factories, for instance. I think that's a super interesting business model. Okay, so let me tell you a little bit about maybe how you would architect that visual motor policy and how you'd do some of this behavior cloning. Right, so there's a kind of a canonical architecture for these things. You tend to have two components. You have your image coming in, and you have some big, deep network, like a ResNet, whatever, something that's trained on ImageNet, pre-trained on ImageNet, for instance, and is good at going from pixels through millions of units into some other representation. And there's a lot of different choices for how you pick the output representation. We've talked a bit about the rise of self-supervised learning as a way to maybe train a feature representation Z. You could just look at objects from two different angles and label them to be the same, and somehow that can cause that can self-supervise a network to represent something important about the scene. Okay, but your choice of Z, that's where all the interesting work is. Like, people are asking, what is the right Z for manipulation? Okay, but it's interesting that because of the computational burden of training a perception system, and because of the wealth of just purely perceptual training data, people typically separate out that massive perception system from a relatively much smaller policy representation. So the neural network that goes from Z and maybe my joint encoders of my robot into my torques tends to be like a 3-layer network with 255 units, right? So I kind of joke when people talk about deep reinforcement learning or whatever, but then they only use 3 layers, and it drives me crazy. Okay, but that's a very standard architecture. In fact, I would say I've talked to people and I said, well, so how many hidden layers do you use? How big is what's your architecture or whatever? And they're like, well, geez, we started using 3 layers with 255 units like 6 years ago, and we never changed it. It's just kind of baked in. All the papers use exactly the same architecture. Okay, that is the architecture that did the kind of stuff I showed you early on. This was an imitation learning pipeline that made super rich visual motor policies for doing things like putting hats on a rack, picking up the plates, pushing sugar boxes or whatever. And compared to the previous, this was the first one we had done. Other people had been doing visual motor stuff, but this is the one that really convinced me. I had to do it ourselves, right? But the robustness that you get out of a demo like that, compared to things that are estimating the location of the sugar box, or which tends to happen only when you don't have occlusions, and then maybe you make a long-term plan and you execute. This is using high-rate feedback from the cameras, trained with imitation learning, which everybody I would say thinks that's an initial startup thing, but not some people would say it's a long-term answer. Okay, but when you're in the lab and you're pushing the shoe, and it's pushing back, and it's so compelling. It is so much more compelling than the things we've done before, right? Where if someone came up and moved the shoe, the robot would be like, still pick up where the shoe used to be, and then it would go through the entire task and drop off the shoe, and everybody's there like, the shoe is still on the table, The airball robot videos are less with this, less. Yes?
Why is it that everyone is using such small networks for the control side?
They seem to be enough. So the question was, why are people using such small networks? So I think in reinforcement learning, that was a choice made early in reinforcement learning, and I think the computational cost of getting enough samples to train a bigger policy network might be significant. So I think if you can get away with a small network, and people have now seen that those small networks are very capable, so there hasn't been a huge push to make them bigger. I think a lot of the heavy work is coming from the perceptual side. I think even in this imitation learning setting, we're often in a setting where we have large corpus of visual data, and relatively you want to minimize the number of demonstrations required. So having less expressive power in the policy can be seen as an advantage. Yes.
But in particular, I'm imagining if a human's too good, maybe, and doesn't get into the same potential failures.
That's a great question. So yeah, so the question is, how do your demonstrations get coverage? There's two aspects of that, I would say. You want, and I'll maybe even cover it a little bit at the end, but having a good enough demonstrator is important, because if someone is a little bit random and they take, from the same image, they take two different actions, then that is annoying. It doesn't fit it's not described as a function. You have to learn multimodal representations and things like that, and that's a real problem. The other question that you're talking about is if the human is only demonstrating sort of the sunny day behavior, then there's a very famous paper about this called Dagger, which they made the point on a Mario Kart driving game. But you're driving along in Mario Kart, you're training, it's by Drew Bagnell and Ross and a few other people. Yeah, if you drive along and you only see examples of the Mario Kart staying in the middle of the road, and then as soon as you go, your training data was just a little bit, you didn't fit perfectly, you find a new situation, you're a little bit off the side of the road, and you never saw data when you're driving off the side of the road, and it just goes whoosh, right off the end. And so the Dagger strategy, which an older strategy of teacher forcing, would be that you tend to not only collect demonstrations, you would collect demonstrations, fit an initial policy, and then allow the demonstrator to try to correct the policy and have a blended control for a little bit, and then eventually let go. So you allow the policy to make some mistakes. The human now has corrective actions. That's one of several answers to this sort of trying to get coverage of the relevant distribution. And that's a response to not trying to cover every state, because that would be a hard problem. Great question. So in that particular work, we used the dense correspondences I told you about before as our Z. So we would actually train dense descriptors, like you did in your problem set, and then we would identify a few, not key points, not labeled semantic key points, but just picked a few random points in the color space, in D, and then find them and turn them into XYZ with our correspondence function. We would use that for our lower level, and that turned out to be I think, we tried to analyze against the other alternatives, and it generated robust controllers and lots of, at a category level. This is what it looked like. So Pete had a mouse teleop at the time. He was really good at it, actually, but we did a couple different versions of it, but on the order of 50 to 100 demonstrations, Pete would just do in lab, whoop, 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 flip a lot of shoes, right? It was actually super useful, if anybody's thinking about imitation learning for their project or anything, to set up the entire imitation learning pipeline in simulation, where it wasn't demanding human users input at all. He wrote a simple controller in simulation that used the full state feedback, and then he just tried to clone that and make sure that all worked. And then you had unlimited demonstrations for free, basically, and you just tried to make sure that you could capture the task. It was using a recurrent network. It needed a recurrent network for some of these tasks, although even tasks where we felt like technically a static feedback controller would have worked well, we still saw better performance from a recurrent network. And this is sort of, coming back to your question, is the generalization power of this was, machine learning folks will talk about generalization versus extrapolation. There's absolutely no claims here of extrapolation. So generalization would be kind of, you're interpolating within the data set that you've seen, and extrapolation would be you're able to do something beyond what you've seen in the data set. And very much the sort of, every way we could think of to make a two-dimensional plot, you could kind of make the convex hull of the training data, and the robot worked really well when it was in the convex hull, and not so well when it was outside the convex hull. Right? And these demonstrations, I think they were so compelling in lab. And this is how we do, dough rolling, for instance, at TRI. And these are places where a few years ago, I wouldn't have even had an answer to the question of what's the state representation for dough? How would I write a feedback controller for dough? Okay, or for noodles. We haven't done peanut butter yet, but we did do sauce spreading. Again, this is kind of the peanut butter, right? This is apparently how real chefs spread sauce. It looked a little weird to me, but we actually studied some chefs and then did it. This is work by Siwan Feng at TRI. Right, and that's a representational question I wouldn't know how to answer, but we're still getting good controllers out. It's interesting, this just came out the other day, so I put it in. There's an article by one of the leads at Google Brain for robotics. He's talking about the push and pull between reinforcement learning and behavior cloning. And so BC is behavior cloning. And then BC methods started to get good, really good. These are links to all his papers. So good that our best manipulation system today uses mostly BC with a sprinkle of reinforcement learning on top to perform high-level action selection. Today, less than 20% of our research investment is on reinforcement learning. It's actually the research runway for BC-based methods feels more robust. That's not what people would have predicted, I think, a year ago. Yeah? Andy Zhang gave a talk at, here at MIT. You hosted him, right? The whole talk was good, but the like second slide was just captured this so well. This the imitation learning. He says how to make a rock star behavior cloning demo on a real robot. Okay, these are the steps. First of all, collect your own expert data. Don't trust anybody else to make it perfect, right? So this is about multimodal demonstrations and some of the subtleties you just asked about. Yeah, avoid no action data. Like that's a weird thing to say. Try not to have anything in your data set where you're not moving, because your robot will get stuck. That's kind of like, there seems like something's wrong with our formulation. If I accidentally pause in my demonstration data, everything breaks. Still not working? Collect more data, right? Until extrapolation becomes interpolation. And the last one's real, right? It says train and test on the same day because your setup might change tomorrow, right? But given that, and these, by the way, I linked to the seminar, and he uses slides.com too, so you can even see his slides. Yeah, but that's real, right? So if you follow steps 1 through 4, you can make some of the best robot demos that anybody's seen, right? But it is important to understand its limitations. He also talks about the hunger for data. So some of the simpler demonstrations where, in the order 50, he's got some really nice implicit behavior. Someone's doing a project on implicit behavior cloning, did some of my favorite examples of these feedback policies for contact, but that was order 500 expert demonstrations, and then some of the rich ones where you're picking up and moving berries and stuff was up to 5,000 expert demonstrations. All right, so this is an opening discussion about control, and I think exceptionally cool that you can do, you can get a taste of what good control would look like. We've learned that high rate feedback from cameras, we didn't know how much we were missing it until we saw what it could do, okay? And I think behavior cloning is a short-term path to study it, and it works incredibly well on real robots, given those caveats. I would say, for me, it's a tool to study the problem and come from the other direction. And as I move up from understanding why underactuated and control through contact and whatever is hard, the misnomer that I don't want you to walk away with this lecture from, right? So the possible impression I could give, but I don't want to give, is that because the problem is hard, you need to use learning. That is one way to do it. But if I give you the equations of motion, and they're just complicated, there's nothing about that that says you have to use learning, right? I think the representational power of deep networks is awesome, but it's not clear you have to take samples in order to optimize them, right? There's many different ways to optimize them, and then we'll explore that over the next few weeks. Okay, I'm gonna call it, but I'm gonna show you, if anybody who wants to stick around for a minute, I did try, in case some of you found it useful for your projects, I made it so you could play with gamepads through Meshcat. And I'm going to play with a gamepad through Meshcat for just a few seconds as we wrap up. All right, this, I'll actually do the non-robot or non-manipulation one first because I think it's fun. Okay, okay, to be honest, I did it first because, I mean, I love you guys, but my kid wanted to use it for FIRST Robotics. So I was like, oh yeah, I thought hard about the problems she was having. And I was like, you should use Drake. Which is crazy, that's not totally, but I was like, oh, I can help you, but I'll do it in Drake. Okay, so this is a mecanum wheel base, right? And it's simulating with the full physics, right? So those are just ellipses. The only way that it's applying torque, it's applying torques to motors, doing velocity feedback on the wheels, and the only way it moves through the world is through the contact forces between the mecanum wheels and whatever. And it's like, it's fun. It's just fun to do that. And you don't have to like install Drake. You just go on Deep Node, and it's I mean, anybody can write a game stick controller. The only thing that was a little clever about it is that we did it in JavaScript and plumb it back through the WebSockets because the JavaScript is the only thing that you're running on your machine when you're running on Deep Node. So the only thing that could touch the Gamepad is the Meshcat browser. Meshcat's listening for the Gamepad if you wanted to, and allowing you to do that. So then, of course, after I did that, I thought, oh, I should do the manipulation station. And I just added to the back of the, so if you want to use this for your projects or anything, I made the manipulation station. Teleop have one more version. If you have a gamepad, pretty much any gamepad should work, I think. It's a pretty standard interface. Oops, I forgot to press a button. So you have to opt in with JavaScript. It won't just read your gamepad without doing anything. So you press the button once. Okay, here's the standard manipulation station. And now I can drive it around with my gamepad. I was saying, I don't know if it's like there's a bunch of tricks for mapping gamepad robustly to like real commands. I've implemented maybe half of them or something. I'm really bad at this. I don't know if it's my brain to the gamepad that's bad or the gamepad to the thing, but it's really hard to do. Okay, but I can definitely pick up a red brick. It's not that bad. So you guys could use this and make it better, hopefully. Oh, I missed. All right. Oh. Yay! Okay, fun. So not quite as cool as like Avatar, but useful maybe? Okay. I'm happy to take a couple questions. I have to run today, but otherwise I'll see you guys next week.